Hello again from Digital Things. As I mentioned in my earlier MECB posts, I wanted to be able to create MECB boards which implemented addressing flexibility. This is to allow any I/O board design to be utilized with different retro 8-bit CPU boards and with different memory maps. This would then support whatever 8-bit CPU-based system design I might want to explore and experiment with. Another consideration is to ideally provide simplicity and consistency to the address decoding schematic, which could then be used as a template across different board designs. In addition, minimizing the PCB board area required to implement the glue logic, whilst maintaining retro through-hole components. When reviewing my old school designs from the early 80s, there was typically a small handful of 14-pin and 16-pin TTL packages featuring in each address map specific address decoding glue logic design. The logical conclusion is to utilize a retro PLD device, which, fortunately, Microchip or Atmel still produce as the ATF16V8 and ATF22V10, etc. Some folk may disagree with this approach, but I believe this is a logical solution for creating a flexible but still retro address decoding design. I would note the following points. Address decoding is about the simplest and most basic use for which you can use a PLD device. Designing your own address decoding logic is as simple as writing an address decoding logic statement. Programming an ATF PLD chip is really just as simple as programming an EEPROM. Many makers who are into retro microprocessors will no doubt already have a TL866 programmer in their toolkit for burning EEPROMs, etc. So let's look at the design. The economical 20-pin dip packaged ATF16V8 appears to have all that we need. In its simple mode, this device has 18 pins available, 8 of which are I/O and 10 are inputs only. In simple mode, 2 of the I/O pins are permanently configured as outputs only, pins 15 and 16. As the ECB bus utilises the memory request and I/O request approach of the Z80, i.e. an allocated I/O address space, my thinking was that I'd utilise 15 pins of the ATF16V8 for inputs, allowing up to 3 pins to be used to chip select outputs. The 15 inputs are divided into the 5 most significant 64K address lines, i.e. A15 to A11, allowing for memory decoding with 2K resolution, the 5 most significant I/O address lines, i.e. A7 to A3, allowing for I/O decoding with 8-byte resolution. And finally, 5 control lines, memory request, I/O request, read, write, and the clock signal. Where this still isn't sufficient for the required decoding, then an individual card design could, of course, still implement some supplemental gates to complete the glue logic, while still maintaining a minimal chip count and still retaining some PLD-based address map flexibility. Alternatively, some control lines could be swapped out. For example, if read and write were not required in the address decoding logic for a particular board design, but perhaps M1 on a Z80 system might be desired. By defining this initial ATF16V8 standard MECB Pin Allocation assignment, this enables it to be included in my MECB standard board design KiCAD template, simplifying the process of designing a new board. If sufficient PCB space is available, it's also worth ensuring that the PCB space allocated for the ATF16V8 can optionally support a 20-pin zero insertion force socket to provide for ease of address decoding swap-outs. In this way, when using an I/O board to experiment with different system configurations, it will be easy to just swap out the PLD for different memory map requirements. Of course, if building a more permanent system, you could just utilize a regular 20-pin IC socket. Okay, well, let's look at the PLD pin assignments. The following input pin assignments have been made. These have been based on the MECB bus pin order of the signals for ease of PCB routing. The 5 most significant I/O address lines, i.e. A7 to A3. Pin 1 is A3, Pin 2 A4, Pin 3 A5, Pin 4 A6, and then Pin 19 is A7. Then we have the 5 most significant 64K address lines, i.e. A15 to A11. Pin 18 is A11, Pin 7 is A12, Pin 12 is A13, Pin 5 is A14, and Pin 13 is A15. Then we have 5 control lines: memory request, I/O request, read, write, and the clock signal. So Pin 9 is the clock, Pin 8 is I/O request, Pin 11 is memory request, Pin 6 is read, and Pin 17 is write. This leaves the following 3 pins available for chip select outputs, noting that pins 15 and 16 can only be outputs. So Pin 14 is chip select 0, Pin 15 is chip select 1, and Pin 16 is chip select 2. So next we'll move on to PLD programming. With the pin assignments determined, the next step is programming the address decoding logic that we require. To do this, I use 2 tools. Firstly, the WinCUPL, or WinCUPL, depending how you like to say it, software provided free by Microchip is used to design your logic and produce a JEDEC format file for programming into the PLD chip. You should find a link to download your copy in the description. You may also want to grab a PDF copy of the WinCUPL User's Manual for your reference. Secondly, I use a commonly available TL8662 Plus EEPROM programmer to program the final JEDEC file into the PLD chip. So let's take a look at WinCUPL. Once you have WinCUPL downloaded and installed, you should see a relatively blank window when you first start up the app. From there, I'm just going to directly open my existing MECB chipselect.pld file to walk through. First, you'll see the file has a header consisting of 9 reserved name fields. These are all the basic header fields, which I understand are all required to be present in the file. But only the name field is required to have a real value in it. It will be used as the default compiled file output file name, so it is logical to just insert the name of your source file here, without the extension. The device field allows you to set the default target device for compilation. You can set this manually via the device selection dialog box, which is under Options and Devices. Here you can see with the DIP package ATF16V8B, or in fact the V8C, both of those are giving a device mnemonic of G16V8A. So I've decided just to use that selected device mnemonic in the device name field. Next, I've created a reminder note that for the ATF16V8 in simple mode, pins 15 and 16 are permanently configured as combinatorial outputs. The actual code then begins, starting with the declaration of the input pins, followed by the output pins, which you can see I've filled in exactly as I described earlier as the desired pin assignments. Now that the pins have all been assigned with appropriate signal names, all that remains is to declare the logic equations we want to apply to our address decoding logic requirements. easy. As you can see, I've created a couple of real-world examples to get us started. But the first example is a simple PLD test, where we simply get our 3 configured output pins to directly follow 3 of the input pins. As you'll see next, I then created a simple breadboard circuit just to enable demonstration verification that the whole WinCUPL to TL866 programmer to ATF16V8 chip programming process is successfully working as advertised. And here is my breadboard creation. I have fitted a 20-pin 0 insertion 4 socket for the easiest swapping of PLD chips. I then have 2 8-way DIL switches to allow switching all of our 15 assigned inputs, 1 switch unused. These simply are pulled high when off via a couple of 10K single inline resistor networks and switched to ground when on to allow for manually pulling each possible input high or low. Finally, I have a Digital Things 8-bit LED thing with the 8th LED simply tied high to act as a power light. LEDs 4 through 7 are all tied low, so they're off, as they are unused. And finally, LEDs 1 through 3 represent the 3 assigned outputs of our PLD, chip select 2, chip select 1 and chip select 0 respectively. In case you hadn't seen my 8-bit LED thing before, it is a little dip module I made several years ago mainly for my experimenting with digital breadboard projects. It does a number of fun pre-programmed actions via 3 mode select inputs, but in its simplest intended use, it enables monitoring 8 digital lines with virtually no signal load, about 1 microamp, using either 3.3 volt or 5 volt power. Total power usage, even with all 8 LEDs illuminated, is only a maximum of about 14 milliamps. I primarily made the 8-bit LED thing as my ideal replacement for the more commonly used simple bar LED with resistors, which are being driven by and therefore significantly loading each signal line it is attached to, plus adding significant load to your breadboard power usage and routing when you have a few LEDs being driven this simple way. The 8-bit LED thing solves all that. Anyway, moving on, I've powered this little breadboard test circuit with a USB-C fly lead, so I can just plug it into my USB-C plug pack, something I seem to be doing more regularly these days, instead of using my benchtop power supply. So back to WinCUPL, under the Option Compiler menu, it's important to check you have the JEDEC selection under Output Files. Then we can select Run Device Dependent Compile or hit the F9 hotkey. All going well, this should give you a dialog box indicating compilation successful and also a .ged file in your project directory. Now to program the .ged file into your ATF16V8 PLD chip. Okay, so I'll just bring in my TL866 2+ programmer, and I also have an ATF16V8B chip, which I'll throw in the programmer. And let's see if we can get this chip programmed. Right, this is XG Pro, the application software for the TL866 2+ programmer. You can see I've got the ATF16V8B chip selected. Normally you'd click on that, search for the device you need, and then select the device from the list. One thing to notice about the PLD chip is there's a checkbox called Encrypt Chip, which is selected by default at the moment. That means once you program the chip, you won't be able to subsequently verify or read the contents. So that protects the content of the chip from being read by other people. You may choose to uncheck that if you like. Let's first load the GED file I just created, MECB chip select GED. Right, with the GED file loaded, let's hit program, and it just confirms the location of the chip in the socket, which I've already got in place. So we'll hit program, erase the chip first and checks it's blank, and then programs it and verifies it. Programming successful. With this successfully programmed, we can then test this logic on our breadboard tester. So let's take the PLD chip out of the programmer, and we'll just move it across to the ZIF socket on the breadboard. Lock that in place. And we'll power up the board. So I've got my USB-C power. Plug that in, and initially you can see we've got, with all the switches off, effectively all of our 15 inputs are pulled high. We can see the 3 output LEDs are all high, the LEDs are on. So if the logic has programmed correctly, switching each of the pins 1 through 3 to on, so they are pulled low, we should see each LED go out, as the 3 outputs correctly follow the pins 1 to 3 inputs. So let's try that out. I'm going to switch pin 2 first, which should take the middle LED off. Yes. And pin 3. And pin 1. And likewise I can turn them back on. Yay! Success! So we have proved that our programming of the PLD is working as expected. So for one final test, let's load some real address decode logic. Let's turn it off. And I'll put the PLD back in the programmer. Okay, back to WinCUPL. I'll first comment out the simple PLD test logic code. Then you'll notice the second example is the decoding logic for the VDP chip in the CreatiVision. The CreatiVision was an early 1980s TV game and computer console. It was based around the 6502 CPU and the TMS9929 VDP for the PAL version. In the CreatiVision, the TMS VDP is memory mapped to use the 2000 hex to 3FFF memory space. Yes, even though the VDP only needs 2 address locations, it was allocated a whole 8K of the address space. This wasn't unusual at the time, as it simplified the address decoding gate logic that was required. Here is the relevant schematic of the CreatiVision, where you can see a 74LS139 dual 1 of 4 decoder is used to generate a VDP read address decode for the address range 2000 through 2FFF. Also a VDP write address decode for the address range 3000 through 3FFF. These are then gated with the 6502's phase 1 clock via 274LS32 to input OR gates to create the VDP's CSR chip select read and CSW chip select write signals. A VDP read is therefore invoked via reading from the 2000 hex address block, and the VDP write is performed using the 3000 hex address block. Of interest, this simple address decoding circuit didn't gate in the 6502's read-write signal. This relied on the system programmer ensuring they didn't issue a write command to the 2000 address block, as this would therefore cause a bus driver conflict with both the CPU and the VDP data bus drivers simultaneously attempting to put data on the bus, potentially overloading the drivers of either the CPU or the VDP chip. We, of course, now have the flexibility of the PLD to fix this potential conflict by including the read and the write signals in the address decoding logic. But for now, I've just emulated the original address decoding logic for the purpose of this demonstration. So in this case, our logic code will use the memory request signal, address lines A15, A14, A13, A12, and also the clock signal to trigger the VDP chip select read CSR and chip select write CSW signals. So I'll now uncomment out the CreatiVision logic block. The logic equation should be reasonably self-evident. There are several ways you could do this, but I have implemented by simply using positive AND logic with the NOT operator, the exclamation mark, to indicate the signals we want active low. I think this makes the logic statement as easy to read as possible. Here is possibly the only section of the manual that you'll need to know to implement this simple combinatorial address decode logic use of a PLD, that is, the logic operators. So first you'll see I've set the chip select 0, CS0, to be active low when memory request MECB is active low and address lines A15 and A14 are low and address line A13 is high. This equates to a memory address in the range of 2000 hex to 3FFF. This is the full address space used by the VDP. This code line is not actually necessary, but as we only need 2 of the 3 PLD outputs for our VDP chip select logic, I thought I'd just implement this for the otherwise unused chip select 0 output. Then I've set chip select 1, CS1, to be active low when memory request MECB is active low, the clock is high, address lines A15, A14 and A12 are low, and address line A13 is high. This equates to a valid memory address in the range of 2000 hex to 2FFF, which is effectively the VDP CSR chip select read signal. Finally, I've set chip select 2, CS2, to be active low when memory request MECB is active low, the clock is high, address lines A15 and A14 are both low, and address lines A12 and A13 are both high. This equates to a valid memory address in the range 3000 hex to 3FFF, which is effectively the VDP CSW chip select write signal. So we'll now update our JED file via run device dependent compile, and we have a compilation successful. And I'll then reprogram our ATF16V8 with this CreatiVision logic, so we can also prove that with a test on our breadboard. Programming successful. So let's once again move the PLD back across to the breadboard. And we'll apply power. Once again, we initially see 3 outputs are high, LEDs are on, while all the inputs are held high. The switches are all set to off. Referring back to the logic code, if we first set A15 and A14 to low, pins 13 and 5, 13 and pin 5, we now have the address selected to cover 2000 hex to 3FFF, but the memory request is still high. If we then switch memory request low, pin 11, we should see both chip select 0 and chip select 2 both go low, LEDs off. Chip select 1 should remain high, as that would also require A12 to be low to signify only the 2000 to 2FFF address range. So let's try it. Pin 11 input, switch low. And there we have it, success. So I think we are now ready to progress to our first functional MECB card, maybe a VDP. But until next time. That's it. Thanks for watching.